Alright, this is our first video in Module 2. So I'm picking up right where we left off from in-class last week. I'm going to try to keep the videos and the in-class sessions in sequence as much as possible. So, enolate reactions, as we began to see at the end of class there, begin as acid-base reactions. So we have the choice of bases, but we don't always have a choice of what is our substrate that has the acidic protons on it. So if we look at the substrate here, we have possibly an acidic proton there, and then we have two acidic protons there. And so these are set. We have a choice of them, but only in the sense that if we use different bases, we can pull off different protons. So in this case, we can control the outcome with the choice of base that we choose. This base is called Lithium Diazopropylamide. The amide part doesn't make a whole lot of sense, but that's the name of it. I've shown the structure over here on the right. The basic part of it is these basic lone pairs. It's essentially a salt, if you look at it, like sodium plus, chlorine minus, lithium plus, and this diisopropylamine, amide, whatever, as the comparable to the chlorine, I guess, minus in that example. So this LDA base can remove either of these two protons here, but it cannot remove this one. And the reason for that is the bulkiness, as we call it. So this is a bulky base. It's sort of self-hindered. You can think of it as getting in its own way. So as it comes in to pull off a proton, it's blocked on this side by the larger methyl group. Literally physically blocked. So these two protons here, either one is equally accessible in most cases. So it will form a bond to one of those protons, abstracting that proton, creating the enolate, as we've been seeing. And it will then selectively, very selectively, create this enolate, which follows from those arrows that I showed you on the left. There is a tiny, tiny amount, I suppose, of LDA that worms its way in maybe and removes that other proton. So we can control the formation of the enolate by the choice of a bulky base. Now we can also vary the temperature, throw in another factor like that, and if we use low temperature, like very low temperature, I'm looking up, you hear the paper shuffling. I guess I didn't have the low temperature written. So low temp, pardon me. So that will further enhance the formation of this enolate because it is what we call the kinetic enolate. And what we have here is what we call the thermodynamic enolate. So when you think about thermodynamics, you think about stability. The more substituted alkene we learned long ago was more stable energetically. So the more energetically stable enolate is the thermodynamic enolate. The less energetically stable is formed through kinetic action, if you think of it that way. And so this is the kinetic or less stable enolate. So the low temperature simply prevents the thermodynamic, it favors the kinetic enolate typically. We'll see some more examples of that. With the less bulky base, much less bulky in fact. So triethylamine, what does that look like? Like that. Significantly less bulky actually. So, and at high temperature, we get predominantly the thermodynamic enolate. So the temperature allows reactions to equilibrate, back and forth until they settle into the lower energy form, the more stable form. Of course, clearly this is aided by the less bulky base, which is able to remove that hindered proton right there, creating the enolate on that side. Still not as good a yield as above, but chemists will take what they can get. We'll take this over a 50-50 yield any day. A couple more examples. Here we vary the substrate, if we're able to, putting a much bulkier group versus, instead of a methyl, a cyclohexyl group. Now this proton is extremely hindered. There's absolutely no way the LDA is going to get in there. And so it's going to proceed in the same way. Create that enolate, virtually 100%, as close to as 100% as we can. Again, aided by low temperature. Just to add a little oomph to it, I suppose. The very small base, KH, so this is like K plus, H minus, it's a hydride base. Hydride's the smallest base possible. And this can easily get in there and remove that hindered proton. And will do so, in fact, so selectively at room temperature because this is the thermodynamic enolate. So with a lot of kinetic activity going on and a very unhindered base, the reaction is going to settle and equilibrate back and forth into the most stable form. Hopefully that makes sense. Thermodynamic. And so these were also good examples of commonly used bases to take note of. Triethylamine, LDA, potassium hydride. We'll see some more examples on the way. So we'll file these bits of information away for future reference. Onward to more enolate style reactions. We're going to march through several classic examples of enolate reactions. Remember how important these are because we are forming new carbon-carbon bonds with some degree of regioselectivity. So with a typical base like sodium hydroxide, probably sodium hydroxide, right? The hydroxide ion can create an enolate through removal of one of those protons. If I had the bond forming, it would do this to create this enolate. I folded the molecule over so that you can see clearly how the next step occurs. This is an intramolecular Aldol reaction. So arrow pushing, these electrons come down. These are the nucleophilic electrons of an enolate. They're going to come in and form a bond to that carbon right here. Kick those electrons up. I should really make room. Well, all right. That's fine. I'll leave it like that. And that gets us to here with protonation assumed as an easy process, right? This oxygen here becomes a negative oxygen, and then that easily can pick up a proton and become your alcohol. We're going to assume protonation and deprotonation steps like that are fairly self-evident because we've seen them so many times. The new bond that was created is right here. It's from the alpha carbon of the enolate to the carbonyl carbon on the other side there. This can then eliminate, as we saw in the Aldol reaction, to create the Aldol condensation. OH is not a great leaving group, but in a sea of OHs, it's a fine leaving group. It's just joining its brethren. as it departs as OH minus. So that's classic E2 elimination, just like in the aldol condensation. And so we get this product right there. Intramolecular aldol. Really, when you think about a lot of reactions that you learn, they can all have intramolecular versions. And ring forming is really important in organic chemistry because so many natural products have rings or sequences of rings, many rings. Okay, that's an aldol reaction. It's interesting to point out that there's an alternative, right? If the enolate, if this would be the other enolate that forms, theoretically, up here, right? So instead of any of these protons being removed, it's actually a result of either of these protons being removed. So you say, how come that doesn't happen? So you get this other enolate possible. It has the same arrow pushing as above to form a new bond between now carbon 5, right, and carbon 2. Notice how I've numbered carbons here to keep track of what carbon is forming a bond to what. This might be the most important tip of the day. With a lot of these enolate reactions and other reactions, you want to number carbons to keep track of what's going where, what's connecting to what. So if 5 bonds to 2, we get this compound right here. And so now we basically have the reason why this doesn't happen. Good old ring strain. Energetically speaking, the formation of a strained 4-membered ring is going to be totally disfavored compared to a flexible, low-energy 6-membered ring. All right, so that's also the reason why 5, 6, and 7-membered rings are most common in nature. And you do once in a while see 3 and 4-membered rings actually, or larger rings, but the smaller ones have ring strain. The larger ones, you have to imagine, how do the ends meet? If it's getting really to be a large and long floppy chain, how do they get to the end, the 2 ends to come together and form a bigger ring? Finally, we have another example of enolate chemistry, important one, that harkens back to to reactions that we did in Organic 2, conjugate addition. So if you want to review conjugate addition, I'm positive I have a video in the playlists Chem 362 videos list. I think there's a whole one on conjugate addition. So Michael reaction, another name reaction. Here's a small base that can form the thermodynamic enolate by removal of that proton. Arrow pushing. Make sure your arrows begin and terminate exactly where they're intended to go. Okay. Anything else means something else, or means something erroneous. Removal of that proton leads to the thermodynamic enolate. So, as we've seen above, a small base leading to the thermodynamic enolate. Here's the interesting part. If we present it with a substrate that is set up for conjugate addition, meaning it's an alpha, beta, unsaturated ketone. Hopefully rings some bells. Remember, the enolate reactivity is like this. Electrons come down. If you need to draw the lone pairs in to remind yourself that they're there, the first dozen times or so, you can do it. The nucleophilic electrons of the enolate are here. Now they, if it undergoes 1,4 or conjugate addition, will form a bond to that carbon right there. And then push these electrons up and away. Carbon can't have more than 4 bonds. Toward the more electronegative oxygen atom, electrons always flow in one direction. They don't crash together in opposite directions. That leads to directly to this. So here I've numbered 1, 2, 1, 2, 3. This is not nomenclature numbering, it's just numbering intended to keep track of what carbons go or stay in one place. So the new bond, we can point out, was formed where? From carbon 2 to carbon 3, right there, that's the new bond. Right, and it's a single bond. The double bond has been pushed up to going between carbons 1 and 2, and these electrons here have gone up onto the oxygen. The base is still hanging around. Oh, by the way, this base is potassium ethoxide in ethanol. So a lot of times you'll see alcohol bases in solution with their associated alcohols. So ethanol ethoxide. Sometimes you'll see sodium or potassium ethoxide. These are strong bases. Small and strong. So with ethanol still hanging around, this enolate can protonate. Can and will protonate. So that reacts, continues to react as an enolate. Notice we created another enolate, by the way. It can protonate itself, picking up a proton from ethanol, and so you regenerate the carbonyl group, and carbon 2 now has 2 hydrogens on it. It still had one before, right? Draw in all your implied hydrogens if you want to, first bunch of times. All right, so Michael reaction, important carbon-carbon bond forming right there. You know, in the days when this was discovered, you know, I think organic chemists probably their eyes grew like saucers, looking at, look how big a molecule we can access in one step. So like this sort of thing. Next up, the Robinson annulation or ring forming. Annulation is ring forming, and Claisen condensation, and generally talking about using creating enolates from esters. Up to now, we've just looked at enolates from ketones. So there's a whole series of reactions using enolate esters, ester enolates. All right.